Welcome back, everyone. So in the previous videos, we have talked about some mathematical expressions that can explain behavior of gases with regards to pressure and volume and temperature and number of moles of gas. And in all of those expressions, we dealt with a scenario where we had some initial conditions and then we had to deal with some final conditions. So our formulas would have things like P1 and P2 in them. Okay, so initial set and final set of conditions. But there is a way to take those laws, specifically Boyle's law, Charles' law, and Avogadro's law, which are sort of summarized here. There is a way to take them and combine them into one big equation that we can use to calculate certain conditions of a gas just at one moment in time. So there is an equation that we can use to calculate properties of a gas at one set of conditions, and that equation is called the ideal gas law. And so the derivation of that you talk more about in Chem 1, but essentially you would take Boyle, Charles, and Avogadro's law. They all have volume in common. If you were to combine all three of those equations into one, you would get something called the ideal gas law, which is what I have circled here. PV equals nRT. So that's the equation that you would use if given just one set of conditions for a particular gaseous substance. Now we're going to talk about what each of these variables in the ideal gas law means, particularly what this R stands for. But let's talk a little bit about what exactly does ideal mean when we're talking about gases. That doesn't exactly, for an ideal gas, that doesn't mean that that gas has all the right makeup and hair products for the time period. To talk about an ideal gases look something like what this cartoon shows on the left-hand side. In an ideal gas situation, you have gaseous molecules. Their sizes are small compared to the space in between the particles. What that means is that there's a lot of space in between individual gas molecules, and therefore that means that the interactions between gas molecules is insignificant. The majority of the interactions that these gas molecules have are with the sides of the walls of their container. Okay? So that would be an ideal gas situation. A non-ideal gas situation is something of like what you would see on the right-hand side of the screen. In a non-ideal gas situation, you can see two differences between non-ideal and ideal. The spaces in between the gas molecules are smaller, so these molecules are closer together. And therefore, because these gas particles are closer together, there is more opportunity for them to interact with each other. These interactions between gas molecules are shown by this blue dotted line. These are called intermolecular interactions. And we're going to talk about intermolecular interactions a lot in chapter 12, the very last section of this course. Okay? But these intermolecular interactions that occur in a gas sample, that's what happens in a non-ideal gas situation. And you tend to get gas behavior like this if you are at low temperatures and high pressures. All of the gases that we are going to deal with in this course and the equations that are associated with them, all of our gases we are going to assume they have ideal behavior. That means we are at high temperatures and low pressures. And if you want to know what I mean by high temperature and low pressure, I've got some qualifications here. You don't really need to know that, but you do need to know the difference between an ideal gas and a non-ideal gas with regards to their behavior. You do need to know those differences. And you should also know that all of the mathematical equations that we talk about in this course with regards to gases assume ideal behavior. So we're going to deal with smiley faced puppy, frowny faced puppy. These are the kinds of equations that you would use when dealing with non-ideal gases. And if you can see, though, you do see some of the ideal gas law, PV equals nRT, in that non-ideal gas equation. You do see some similarities. But we are not going to deal with frowny face puppy in this course. All of our gases will be ideal, and so we will be using the ideal gas law. So let's talk about just a little bit about the variables associated with the ideal gas law, and in the next video we will do a sample calculation. So this ideal gas law, PV equals nRT, you could probably already guess. You know that P is going to be pressure, V is going to be volume, N is going to be moles of gas, T is going to be temperature. And once again, when we talk about temperature with regards to gas laws, it must be expressed in the Kelvin scale. So you'll take your degree Celsius and add 273 to it. But let's talk just real quickly about this new variable that you see in this equation, which is R. This is the proportionality constant that's used in the ideal gas law, and it's called the gas constant. And so this value of R is what you will always use in your problems when you use the ideal gas law. So you will always use this value of R when doing those kinds of problems. And so you can see that the units of R kind of has funky units, right? It has 2 units in the numerator and 2 units in the denominator. This is just because of how it was derived, which you talk about more in Chem 1. But what you need to be aware of and cognizant of when doing gas law problems using the ideal gas law is that because of these units on the gas law constant, because of these units, your pressure that you use for the ideal gas law must be in atmospheres because of the units in the gas law, or because of the units in the gas constant. So your pressure must be in atmospheres. Your volume must be in liters, and obviously your amount of gas must be in moles. So that's a little bit of background of the ideal gas law. In the next video, we will do a sample calculation that's talked about here, but we will do it in detail, this sample calculation about the ideal gas law.